The Big Bang is the prevailing cosmological model explaining the existence of the observable universe from the earliest known periods through its subsequent large-scale evolution. It is also widely accepted as being the beginning of space and time. However, there is one problem with this grand idea. It cannot explain the Big Bang itself, or the conditions that created it. For over a century, the theory of the Big Bang has been argued and questioned, but it is only in the recent years that there has been a shift in how the Big Bang theory is viewed. What if, instead of being the first event in the universe's history, the Big Bang was actually just one phenomenon among an infinite sequence of events? Roger Penrose is a British mathematician, physicist, and Nobel laureate in physics. He argues that the Big Bang was not the beginning. There was something before the Big Bang, and that something is what we will have in our future.
Einstein's equations require what's called a cosmological constant. It's usually called lambda. These days people call it dark energy. And it causes the universe to expand and expand and expand. And this behavior is in all the cosmology books. If you put in this lambda, the cosmological constant, and when it's positive, that's what it does. So that's pretty well a picture of the universe as we now believe it to be, except people usually think right at the beginning there is something called inflation. This inflation was supposed to have taken part in the universe's activities in the first about 10 to the minus 32 seconds. So think of 1 followed by 32 zeros. 1 over that fraction of a second, in fact, is supposed to have been within the time that the inflation took place. You see, this expansion looks very much like what we see now as this exponential expansion of the universe from the observation of distant supernova stars and all sorts of other things which fit together to get the picture that that's probably what the universe is doing now. But this view is that within these first 10 to the minus 32 seconds, it did this other exponential expansion and expanded by some huge amount in that tiny little point. Now, I never liked this, partly because it didn't fit in with Einstein's equations very happily, partly because, well, it didn't do half the things that it was supposed to do. It's supposed to smooth out the universe, and it doesn't do that. However, if we don't have inflation, you've got to have something a bit like it.
Cosmologists have made many presumptions and hypotheses that have looked deeply into these factors that include dark matter, dark energy, several inflationary cosmological models, and inflationary cosmology. According to Penrose, however, proposals for describing the initial state of the universe hardly ever address a certain fundamental conundrum. Yet, this is a conundrum whose significance is, in a certain sense, obvious. The issue arises from one of the most fundamental principles of physics, the second law of thermodynamics. According to the second law, roughly speaking, the entropy of the universe increases with time, where the term entropy refers to an appropriate measure of disorder.
The second law of thermodynamics, what does that say? It says, more or less, things get more and more random as time goes on. The measure of randomness that's being used here is a thing called entropy. And the second law of thermodynamics tells us that entropy is increasing all the time. Now, that means to say the entropy increases with increasing time is the same thing as saying entropy decreases when you go back in time. So I'm just saying the same thing. So it goes down and down and down. But if you go back and back, way back into the past, where do you get? Well, you get to the Big Bang. Now, the Big Bang, what's the best evidence for the Big Bang? Well, they have this cosmic microwave background, this radiation, electromagnetic radiation, light, like a microwave light, coming in from all directions. And it has a certain spectrum. That is to say, you look at the different frequencies and you look at what the intensity is for different frequencies. And this shape of the curve you get is an extraordinarily close fit to the Planck curve.
There are many popular theories among scientists that suggest that the Big Bang was not the beginning of our universe. The many worlds interpretation, which is one of many multiverse hypotheses in physics, implies that there are very many universes, perhaps infinitely many. Penrose argues that the idea of many worlds is flawed because it is based on an oversimple version of quantum mechanics that does not account for gravity. According to Penrose, the rules must change when gravity is involved.
In my view, what's wrong has to do with gravity. See, the idea is that if you consider what happens when you bring gravity into the experiment, you realize that there is a conflict between the rules of quantum mechanics and the principles of general relativity. And the principle of general relativity that I concentrate on mainly is what's called the principle of equivalence. And that says that a gravitational field locally is the same as the effect of acceleration.
An alternative theory proposed by Roger Penrose is called the conformal cyclic cosmology. The theory basically assumes that there is no multiverse, but rather only one universe. The idea behind eternal cyclic cosmology says that our universe will continue to expand until it reaches a big crunch, after which another Big Bang will occur, and so on. The cycle repeats endlessly.
So here we have our eon, that's our Big Bang. The initial expansion slows down a bit, and then the exponential expansion in the remote future, which keeps on going indefinitely. And that infinity, or eternity if you like, is squashed down into a finite boundary. And what I'm saying is that this finite boundary looks very much like another Big Bang. So that there was before us an eon, and that eon had its Big Bang represented here. It expanded indefinitely, that squashed down, its infinity becomes our Big Bang, and then this is our eon, and then our remote future will become the Big Bang of another one. And these continue maybe indefinitely.
Penrose's conformal cyclic cosmology, or CCC model, is an extension of general relativity, but opposed to the widely supported multidimensional string theories and cosmological inflation following the Big Bang. Penrose postulates that at the end of the universe, all matter is eventually contained within black holes, which subsequently evaporate via Hawking radiation.
Our galaxy has a black hole which is about 4 million times the mass of the Sun. There are lots of smaller ones undoubtedly going around, but the one at the middle is extremely big. Now, what happens to the black holes eventually? Well, as you see, they evaporate away by Hawking evaporation. And then when they've all gone, how long does that take? Well, for the really big ones, you have to think of something like a googol years. What's a googol? Well, that's 1 followed by 100 zeros. And that's the sort of time you're going to have to wait before all the black holes have gone. The really big ones take the longest to go away, and the smaller ones go away much more quickly. But after they've all gone, now I thought it was pretty boring before, sitting around watching for a black hole to evaporate away. Now that's dead boring. When they're all gone, that's very boring. But then I began to think, who's going to be bored by this? Well, photons probably, mainly photons. And it's really hard to bore a photon. It's hard probably for 2 reasons. One is it probably doesn't experience anything. But the other is from relativity effects, photons don't experience time at all. The time from creation of that photon or whatever happens to it is nothing to that photon. So that it gets right out to infinity, and it's as though this just happened instant.
Critics have levied towards several parts of Penrose's theory. Penrose himself has admitted that his model is extremely speculative. The conformal cyclic cosmology theory lacks a mechanism for explaining the temporal asymmetry in our observable universe. The early phase is very different from the late phase, even though no such difference is to be found in the fundamental laws of physics. Science can't make progress without questioning existing theories, and it's inevitable that wrong theories are developed during that process. It is this process of questioning and testing that has given us many of the technological advancements we now enjoy, and they continue to make our lives better in countless ways today. Thanks for watching.